This is fluid mechanics.
Good. Okay, so welcome to video number 7 in fluid mechanics. So in this video, we're going to be starting section 3 now, which is called integral control volume analysis. And as we just finished off section 2, what we did there was to look at the forces exerted by fluids when they're just stationary, they're not moving, so that was fluid statics. Now in section 3, we're going to look at what happens when they're moving and when they're flowing. And so in this case, we're going to look at the forces on control volumes, which is like a defined region of space. And so we're going to see now how to calculate the forces exerted by fluids when they're moving. Okay, so in this video, we're starting in on section 3 now. And this is titled Integral Control Volume Analysis, which isn't really a descriptive title, but I'll explain why it makes sense to use that in a second. We can also think of this section as being really about mass balances and force balances. Okay, and we're going to cover 3 subsections in this video. So firstly, in 3.1 there, what we're going to do is we're going to take a look at the basic laws for a system. So that's like conservation of mass and Newton's second law. Then in 3.2, what we're going to do is we're going to take those laws that are based on systems and we're going to convert that. We're going to see how those change. So what equations we have to use when we're dealing with control volumes instead, because they have mass crossing the boundary. When we have fluid motion, right, we can have flows that enter and exit across the control volume boundary, which is called the control surface. And then in 3.3, we're going to look specifically at conservation of mass. So we're going to do like a mass balance over a control volume. And then in a subsequent video, which really we can think of as like part of this video, we're going to do example 3.1. We're going to look at flow through like a pipe style system with a port on it, and we're going to do conservation of mass through that and see how we can figure out different flow variables like velocity. Now, adding flow makes the analysis a little bit more complicated than the static side of things, right? So let's first look at, there are 2 different approaches to studying fluids in motion. So there's what's called the system approach, and what we're doing here is we're following around all the particles as they flow around. So an example of that might be, say there's a factory and it's emitting pollution out of one of its stacks. And so you're interested in tracking the particle motion of this pollution to understand, where it disperses, where it flows after it exits the factory. You want an understanding of where it's going, so you'd follow the particles around, right? And to accomplish that type of analysis generally means you need partial differential equations, and the math is a little more complicated. So that's not what we're going to be learning in this course. There are more advanced fluid courses where you look at that in more detail. So for the types of applications we're interested in as engineers, right, in looking at the mechanics side of things, we're going to use a control volume approach. And the control volume approach is a very practical approach. And basically what you're doing here, instead of following the particles around, you're interested in a region of space. So you pick a region of space, that's your interest point, and then you look at the influence of the flow on that space, right, in terms of the mass flow and the forces, which is what this section's about, right? So this could be things like you draw a control volume around a wing, for example, or a rocket ship. These are the types of things. I'll go through a few examples of applications in a minute here. And the only thing we're going to have to do, though, is the laws that we have, the laws of physics that dictate how these things behave, they apply to matter, not a region of space. So we're just going to have to do a little bit of math here to convert between the system side of things versus the control volume, but that's not too bad at all. So I'll go through that in this video. We'll look at how we have mass balances and force balances over control volumes, and then I'll do it as a separate video, but as part of this video here, I'm going to do an example right after that of a mass balance. Okay, first example we'll look at for applications is a rocket. And we'll actually do a rocket question. I'll do it as an example in one of the upcoming videos. So I'm showing here a launch of one of SpaceX's rockets. And essentially all the major forces at play here is fluid mechanics. This is everything that we're going to do in this section 3 here. The fluid coming out the bottom is called thrust, and that's what moves the rocket upwards, and then any resistance to flow it has we'll cover in a later section of this course. But for now, the forces propelling the rocket upwards is what we're going to look at. Another one is firefighters, right? So people underestimate sometimes how challenging it can be as a firefighter. So here's an example of where you see the tremendous forces at play in this video I got off YouTube here. So that's another thing we'll look at. So what's happening here is there's the forces from the fluid coming out of the hose and the forces exerted like back onto the hose where the firefighter's trying to hold it. And we could also have the force from the fluid stream itself, right? So you'd have a hose knocking things over. So we know there's forces at play there. We're going to look at that as well. And another way we use that is turbine blades, right? So turbines take advantage advantage of a flowing fluid. We think of air, right, for the wind turbines we see, but there's also many, many turbines that run off water as well. And so that's an example, again, of like flowing fluid exerting a force onto the blades and causing it to rotate, and we harness that energy, right? Okay, so now we're going to look at these basic laws for a system that I referred to above. So we'll start with conservation of mass. You're probably familiar with this, right? Basically saying mass can't be created or destroyed, so we have a conservation of the mass in a system. Now, just as a reminder, I've put a little picture on the left here of our system, and so a system is defined again as the mass, right? So we can't have any mass crossing the boundary. So for conservation of mass, this is a really important part of this course. What we're going to do is take these words, right? So I can describe in words that mass is conserved, and we're going to put that into equation form. It's a big part of engineering. This is one of the first courses where we really focus on doing this. So I'm going to write what I just said as this dm by dt for the system equals 0. So that expression right there. Now, let's just think about for a second why that expresses what I just said. So we're saying the dm by dt, if we remember from calculus, right, that's a derivative. And what that's saying is dm by dt describes the change in mass related to our time. So it's saying that's the rate of change of mass. How does the mass change over time in a system? Well, we know system is defined as a quantity of mass, and you can't have any mass crossing the boundary, so there is no change in mass over time. That's how it's conserved. It can't be created or destroyed, so that is equal to 0. And then we're just going to have one line below it. I want to make sure we set everything up here before we have to go into our analysis below and this is a nice reminder of some of the calculus we use here. So this is where it's important to, as an engineer, to not have a fear of some of these calculus expressions. Because again, Newton created this to describe these things. These are our equations, right? So when I write the mass of a system here, one way to describe that is in integral form. And this relates to the fact that we're not dealing with systems, we're dealing with control volumes. So it's something we're going to need to do here. And the first step here is to say, how do I express the mass of a system as an integral? And we can essentially remember integrals are summations, right? So if I sum dm, right, differential quantity of mass over the entire system, that leaves me with the mass, total mass of the system. Now, another way I can write that, so that seems obvious, right? But a more useful way to write that is to actually integrate over the volume, right? You can see where this is going, I think, because we're going to talk about control volumes. So in this expression here, right, we now split up the mass into density. So if I integrate the density over the whole volume of the space. Now the density is the mass divided by the volume. So if I take the values of the density, right, and I sum them up over the entire volume that I'm dealing with, right, that's going to leave me with the mass over the total volume, and I multiply that now by the volume, which is what this expression says here, and I'm left with the total mass in the system. We're going to see that's an easier way to write this expression, so we can actually use it. As engineers, we want to use it, right? Now Newton's second law. So let's go down to Newton's second law, which again, we're familiar with from physics. I think we've seen this before, basically saying, F equals ma. That's what we think of it, right? But again, now we're going to look at this from a more technical standpoint, from an engineering standpoint. And what Newton's second law actually, when we write it in equation form, we have this equation right here, where the P there is actually denoting linear momentum, okay, which we, again, might remember. So that's mass times velocity. So we can see, again, if we look at this, so force is now equal to, so we would have thought that would have been mass times acceleration, but actually a slightly more precise way to write that is the rate of change of linear momentum. If we think about that for a second, so P is m times v, velocity, right? So it's really saying the same thing, because if I multiply m by the rate of change of velocity over time, well, that's acceleration, right? So you can see it does kind of solve to the same thing. But this is a form we're going to need as engineers. It's actually the rate of change of linear momentum in the system. So what you'll see often, so again, feel free to be taking your own notes here, right, to help with retention. But essentially what we're doing with Newton's second law is, I'll refer to it as like a force balance, or, which is really the same thing, we would also say a momentum balance. So if you see that, right, momentum balances are really force balances. Okay, and again, that helps to prevent us from confusion later down the road. And so again, we have the same kind of idea. Now we're going to need to write this system quantity, like this linear momentum here, in a volume, for a volume, right? So we would, in a mass basis, right, when we integrate, we would take integrations like a sum, right? So you'd take velocity times dm, that'd be velocity times mass, and that would get you the total linear momentum of your system. but we're going to want it in volume form. So again, we do the same kind of manipulation here, where instead of mass, we're going to write density times the volume to get our mass. And this V here is velocity, right? The ones with the slashes are volume. Okay, so we're going to have this quantity for the volumes here, and then this is how we're going to end up writing our linear momentum. When we integrate that and we integrate that over our total volume, we end up that's like mass times velocity. Okay, now in the past, so there's a lengthy derivation here that gets us from our system frame of reference into our control volume frame of reference. And I did that the first few times I taught this course, but I realized there really isn't a point to that. If you're going to be using that type of derivation in the future, it's something you can learn in more advanced fluid mechanics classes. For the purpose of what we're doing here as engineers, we don't need to do this derivation. So this is an example of where I'm going to skip the derivation of this, but I want to show the equation that results, okay, and not bother with the derivation. But, we're going to want to be able to use it. So what I'm going to do is go through the terms in this equation so that we understand what they are, what they mean. And that way, when we come to actually calculating things, we know what to do. This is where I want to put the emphasis for this course. This is what I think is a little more important than, deriving these equations. So let's do that here. Let's look at these terms. So this is the equation we're looking at here is the conservation of mass for a control volume. Okay, whereas up above what we had was for a system, right? So at the left, I've just shown as a bit of a reminder, right, what a control volume is. So that would be for a little bit of a piping system here. The control volume is the dashed line. I'll show that in green again, just so it's clear. And the difference again being that in this control volume, right, we do have mass crossing the boundary. So that's the big difference here, right? We have flow entering and leaving. And as engineers, we're going to want to calculate the forces on these things. That's the purpose of this. So let's go through this. So we want to so the laws apply to our system, right? So we've looked at, let me do this in different colors here. We've looked at this first term already, right? And we know that means dm by dt is the rate of change, so the change in mass over time, right? That's what that quantity means. It's how mass is changing over time. And for a system, right, that's 0. So I'll put the words here, right? So rate of change of mass and a rate of change, right? That's over time, of course. I'll put that here just so we remember. And I will make a little note, right, that this term is referring to a system. So we said mass is conserved, right? So that's going to equal 0. Okay, now let's look at this one here. So what is this one accounting for? So this is where I want to do this in steps, right? I think too often engineers are really turned off by these calculus expressions, and it shouldn't be the way. They're fairly straightforward. So what I like to do is just probe each individual part of this, right? So we're really comfortable with it. So I'm going to use yet a different color. So basically what's saying here, this right here, this partial with respect to time, that's saying that whatever's to the right of it now is going to be a rate of change over time, okay? So what is this thing in the brackets? Well, so we've seen that before. So this CV refers to control volume now. When we see that, that's control volume. Okay, just abbreviated. And then we're having density integrated over the entire volume. Okay, and density is mass over volume. And then we multiply that by volume as we integrate over the whole control volume. So we end up with mass. Okay, so what this term is then, so that's the rate of change again, because it's di by dt. We just figured out that the density times the volume is mass. So that's the rate of change of mass. And this is in the control volume. And just for completeness, just the part right here, just so we remember, that's the instantaneous value of, in this case, mass, right, in the control volume. Alrighty, and so the d by dt in front of that makes that a rate of change, right? Now, go down my color palette here for this last one. This one's really interesting too. Okay, so what this last one is an integration over, in this case, even a different color here, CS is a control surface, right? A control surface. So in the picture I have to the left, 1, 2, and 3 are labeled there. So for example, like control surface 1 would be like that guy there where the mass is crossing, right? So that gives us an indication of what we're going to be dealing with here. So it's rho V, density times velocity, dot product with the area. Okay, so what's going on here? Again, that's not something, I mean, maybe some of you do, are okay with this, but a lot of people don't like this type of calculus expression. So what we're going to do is we're going we're going to look at it very closely and we're going to take power over it, right? So one trick to use for this, let me go to a different color again. It's going to be like a very colorful page here, is to do the units, right? So if I want to figure out, so what is the density times the velocity times the area here integrated over the control surface, I can quickly look. So density, right, is in kilograms per meters cubed. So the units might reveal something here. Velocity meters per second, right? And then times an area, okay, which is meters squared. So what do we end up with? Meters cubed on the bottom, meters cubed on the top. I can cancel those. So we're left with kilograms per second. Aha, which is the units of a mass flow rate, right? So that gives us an indication that what we're having here. So if I multiply the density, right, times the velocity times the area, I end up with the mass flow rate, right? And this, so when you have velocity here, velocity times the area it's flowing over, that's actually another way of writing volumetric flow rate, which we can see from here. That would be meters cubed per second, right? Times the density, so volumetric flow rate times density gives us mass flow rate, kilograms per second. So integrating over the control surface means that we have the rate at which the mass is exiting the surface of the control volume. So that's what that means there. Rate at which mass is exiting the surface of the control volume, which we call the control surface, CS. Okay, so this expression then is how we write it in control volume, and we're going to look, the whole next section is going to be mass balance, so we're going to see how we use this, right? And then afterwards we're going to do, in another video, we're going to do it for momentum balance, which is like a force balance too. So, well, firstly, why did I say exiting? Maybe some of you are like, why exiting? Rate at which mass is exiting the surface of the control volume. So the answer to that, we can actually go back to some earlier math you may or may not remember. So I'm going to show it again here at the bottom. So when we have a dot product, right, with these vectors, you remember, so I've shown dA here, right, where dA, we remember, is normal to the surface that it's talking about, right, so that's the vector shown there, and we have the velocity, right, and so the angle between the two is alpha. So in this case, where we have velocity exiting this control surface, it's not normal to the surface. So what we would write for v dot dA, we remember it's the magnitude of v times dA times the cosine of that angle. So that's this one here. That's in the general case there. So if we look at the case where it's normal, B is normal exit, right? So the angle between the two is now 0, right? So the velocity and the dA vector are both normal. So that's just a positive quantity. So that's why the way this is written, right, where this term here is positive, when it's positive, that means exiting, right? So that's an exit right there when it's positive. And then if we have the velocity entering the control surface, case C right here, now the angle between them would have been the 180, right, which gives us the negative value. So it's now negative VDA, right? So if something is entering, then that dot product will yield a negative value, right? And that's the dot product right here, okay? And so when we're solving these, that's how we'll remember it. We'll see v dot dA, and we'll remember that if that's a quantity that's entering the control volume, we have to write that as negative. We'll see that in the examples too. Don't worry about that. I'll do that in the examples as well. Okay, so let's move on. So let's look at mass balances, how we're gonna use them. It's really what's important for us as engineers, right? We want to learn how to solve problems with this, how to figure things out. So this is the expression we had from above. We're now in section 3.3. We're going to look at this very specifically, conservation of mass. Okay, so as we described above, right, the conservation of mass law says that for a system that is equal to 0, okay, so we'll get rid of that term. Okay, now on the line below, we've written that's equal to 0, and then what we do is we simplify. Okay, and we're going to look at this simplification for a second here. Now we remember on the left, that's saying the rate of change of the mass within the control volume. Okay, we listed that above. And again, keep your own notes here if you need to write that again. That's the rate of change of the mass within the control volume. Okay, so if my control volume is a bucket and I'm filling it with water, right? That's the rate of change of the water, of the mass of the water within the bucket. Okay, now on the right here, okay, this is how things cross control surfaces, okay? So that's the rate at which mass is entering or exiting our control volume, right, across the control surfaces. So now you might think that is painfully obvious. So again, if I have the bucket, I'm filling the bucket. So on the left, that says how much the mass of the water is changing within the system. And on the right, that says the rate at which mass is entering. So the flow rate of that water crossing into my bucket control volume. Maybe I'll sketch that here. That's my bucket. I might draw the control volume around it like this, right? And now I might have some water in it, and I might have some water flowing down, right? So the first term, that's like how much that mass within the control volume is changing. And this term right here is looking specifically at right there where it's crossing the control volume. Why don't I use a different color? Right there, right? And you're probably thinking, yeah, no kidding. That's fairly obvious, right? But it's important to write this mathematically, and we'll use this expression because not all questions are this easy. So that essentially that's what the expression is saying, right? And you can see why the calculus just isn't that bad. That's what that expression is saying mathematically, what we just said in words. Okay. Now, as I keep mentioning, engineers don't really like to use integration all that much. I myself fall into that category. I think if we didn't have to integrate, we'd all be happier, right? So we're going to simplify this expression so we don't have to use it in this integral form. This is just the most general way of expressing conservation of mass for control volumes. So I'll look at some special cases below, and we've talked already about incompressible fluids. And what that means, again, we remember, is that the density is constant, and we generally use that for liquids, right? But also gases too when we don't have a big change in density. So lots of cases, almost everything that we're going to want to consider in this course falls into the incompressible category. So what we can do there, so density is constant now, right? So I can pull the density out. So the density used to be here. I can pull it out front now of these integrals. We don't have to integrate our constant values, right? We only have to integrate things that change over whatever we're integrating. So now if I pull the density out front, what happens here is the quantity on the right is 0, so density multiplies the whole term on the left, and we know that density itself is not 0, so the other terms have to be 0 to make that expression true. And now this term here, right, that's just the integral of the dV over the control volume, so that's just the volume, right? That becomes this term here. And now if we pause and think about that for a second. So like the example of the bucket above, for example, like I've drawn the control volume around the bucket. Well, like you will decide what the control volume is. So we've decided what the control volume is there. So this is saying that control volumes change over time. The change in the volume over time, dV by dt, is what that's saying. So when we have a control volume that we decide on, normally they're non-deformable. Like normally they're over objects that are solid, right? So we say we have a non-deformable control volume of a fixed size and shape. And so that is going to be equal to 0. We don't have, that's just the change of the volume over time. So if our control volume is non-deformable, it's fixed size and shape, it doesn't change over time. So then we just end up with this expression here. Now this is the one we want to box quite a bit, right? So what that's saying is that is the conservation of mass for a control volume for incompressible fluids, right? So that one will always work as long as we're dealing with incompressible fluids. There's still an integral in that, right? So let's talk about what the integration is for, what it means, okay? And then we're going to figure out when we need it, when we don't, right? And ideally, we're going to want to not have to use it in most cases, which is where we're going with this. That's where we're headed. So let's walk through that. Okay, let's dive in on this one and look really closely at what this means, okay? So when I say I'm integrating the velocity over the area, right? So over the control surface here, I'm integrating this term over this area here, which is our control surface. So the only times you have to integrate that is if the velocity is changing over the area. So let me just draw, I'll just draw kind of like the end of a pipe here. And what would happen in most cases is the velocity profile would look something like this. We've seen one of these before. We'll get into more detail of this in later sections, but essentially it's slowest near the wall and it's fastest near the middle, which is true for laminar flows mostly. So in that case, we can see, so these right here, this is the velocity values, right? In green, that's our area, that's our control surface, our area that we're integrating over. So I only need to integrate when this velocity changes over this area, okay, which like we've seen is going to be a lot of cases. But I could skip the integration if I had a way of writing a uniform velocity or an average velocity, right, that took into account this integration already. So let's look at that. Okay, so I'll jump to a fresh slide here. So we're saying I've written the incompressible one here, and we're saying we only have to integrate when the velocity changes over the area. So if I instead write a uniform velocity, instead of having to integrate, right, I can just use this expression here, which is a summation, okay, over each of the control surfaces. Okay, so in that pipe system I showed above, we had the 1, 2, 3. There was 3 of them. In the example I'm going to do right after this video, there's also 3. So that's the summation over each of control surface, right, of just the velocity times area. And it's a dot product, so we remember when we need to make it negative and positive. Basically, that's why the dot product's there, okay? If we just super simplify this thing. So this is the one we're going to be using like 99.9% of the time. So I am going to box this, right, in different colors. I'll do whatever, like I've got a highlighter here. Let me that needs maybe a pink highlighter. This is the expression right here, okay? That's the expression we're gonna be using. Okay, now, why would we have a uniform velocity? Or why would we have an average velocity? So it turns out that in a lot of the cases we're solving for, the variable that we're gonna be describing is normally the volumetric flow rate, right? So this here is volumetric flow rate, meters cubed per second. And in the systems we deal with, that's something you know, because normally that's something that you need to design for. You'll need a certain flow rate, right? If it's a house, you need how much flow they're gonna need when, for example, they're showering or watering the garden or whatever. Volumetric flow rate tends to be the variable that you design for as an engineer. So we know that ahead of time. And actually it turns out, right, like we talked about before, that the volumetric flow rate really just is the velocity times the area integrated over the area. So this, if you have this Q value, the integration has technically already been done, right? Because you'll have that Q value, okay? And then to turn that into a velocity, right? So let's look below here for average velocity. If I want the average velocity, all I have to do is take the volumetric flow rate divided by the area. That right there, again, I don't know how to emphasize this, lots of arrows maybe. Not too many, so you don't question my sanity, but yeah, this is how you do it. So you'll know the volumetric flow rate divided by the area it's flowing over, and that gives you this one right here, right? And normally, so we'll write that as like V average AVG or something like that. And you can see the integration has already been done for us, right? It's already been taken care of. So in questions, right, if you have the volumetric flow rate, just divide by the area, you have an average velocity, and then use this expression right here. This is getting a little crazy. Yeah, okay. So not box that too many times. Okay, so that's the expression. That's the easy one to use. That's the one we love as engineers. And of course, we remember to use that. We just have to make sure it's incompressible, okay? And we just have to make sure that we have an average velocity or a uniform velocity, okay, over the surface. That's it. Those, generally, it's easy to check those boxes. We normally do have those things, right? So that's the expression we use. Now, we can't forget about compressible flow, of course, just for completeness, the following two equations down here. So in compressible flow, one way we can simplify it is by saying we have steady compressible flow, because that's something we'll commonly have. And if we have steady compressible flow, and the first term in that expression was d by dt expression, right? So for steady, we only keep the second term, so we'll end up with this expression here, which is a little more easy. Because the density changes, we're not going to pull it outside of our integral, so the density is left inside there, just notice that. And then again, if we don't want to have to integrate, right, so we say steady compressible flow and uniform velocity, right? So if we don't have a change in either of these expressions, velocity times the density over the area, right, then we can simplify from our integration into our summation here, okay? So if you have uniform velocity and density not changing over that area specifically, we can write it like this in summation form instead of integration form. Okay, same trick like we used above. That's just for steady compressible flow. Just notice the density we have kept in there. We have to keep the density in there because we weren't able to pull it out front and simplify. Okay, so that is everything. Now, normally I'm going to feed right into an example here. So try to watch this example as close to this video as you can. I'll do an example for a mass balance calculation on a little piping system with a port in it, just to see how we use this, right? I think that's really important to see how we use these equations. And that's it. I guess I'll do a quick summary because I often get asked for that. So basically in this lecture, we talked about section 3. Okay, and basically we're going to be doing mass balances and force balances over control volumes. Okay, so we call that an integral control volume analysis, right? Because as engineers, what we're concerned about looking at is control volumes, okay, which is a location in space that we picked out. Normally it corresponds with a wing or a rocket or something like that, something we want to know what the forces are on it. Okay, so in this lecture we went through the equations, we talked about how the laws apply to matter, right? And when we look at a control volume, the only thing we really need to do is we need to talk about balancing the rate of change within the control volume with all the different quantities that can enter or leave a control volume. Okay, that was like the bucket example. So the amount of water in the bucket can change as a function of how much things are flowing in or out of this bucket. So we looked at all the equations, different ways to simplify them, how we can have very simplified forms if it's incompressible or uniform velocity, and that's a much easier way to solve problems instead of the integration form. Yeah, and now we're going to look at an example. So that's everything for video number 7. Thanks.
Bye.